Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to explain how to describe a continuous random variable using its cumulative distribution function, which encodes the probability that the random variable belongs to any interval on the real line. We will also explain the connection of the cumulative distribution function to quantiles, and we will explain how to estimate all of these quantities from data. Let's get to it. The plan is to define the cumulative distribution function, then define the quantiles of a distribution, and then explain how to estimate them from data. Remember that mathematically, continuous random variables are functions from a sample space to the real line. But in practice, we don't want to talk about this underlying sample space. We just want to describe the random variable in terms of the probability that it belongs to different intervals on the real line. And in the video on the mathematical definition of continuous random variables, we saw that this was mathematically legitimate. If we know the probability that a continuous random variable belongs to any interval on the real line, we can just describe its behavior using those probabilities. But of course, that begs the question, how do you encode the probability that a random variable belongs to any interval on the real line? This seems kind of difficult. We cannot have just a list of intervals and the corresponding probabilities like we did for discrete random variables, where the probability mass function is essentially that. It's a list of the probabilities that the random variable is equal to each of its possible values. We cannot do that for continuous random variables because we're interested in intervals and there's way too many intervals. So what can we do? Okay, how do we encode this information? Well, we encode this information defining the cumulative distribution function of the random variable, or CDF, which we denote by a big F with this subscript that tells us what random variable we're talking about. The CDF tells us the probability that a random variable is smaller or equal to any value on the real line. And we will see that this is enough to encode the probability that the random variable belongs to any possible interval. Okay, in words, it's just the probability that the random variable is less than or equal to any value on the real line. Let's take a look at the basic properties before we explain why it encodes the probability of being in any interval. Okay, so let's think about the limit of the CDF when we take this value a to infinity. So if we draw the real line, the CDF tells us the probability of being here up to whatever value a has. But if we take a to infinity, what's going to happen? We're going to get the probability that the random variable is anywhere on the real line, and that probability has to be 1. Similarly, if we take the limit towards the left, in the end we end up with the probability that the random variable is smaller than an arbitrarily small number, or arbitrarily negative number if you want. Eventually that's just 1 minus the probability that the random variable is anywhere on the real line. Because remember that we can reason in terms of disjoint intervals. The probability that a random variable is equal to, maybe let me go back here. The probability that the random variable is in the union of two intervals, let me draw a quick picture, is equal to the sum of the probability that is in each of them, right? So now what I'm getting at is that if we take this a to minus infinity, the CDF tells us the probability of being in the green segment. Eventually it's going to go to 0 because this blue segment is going to take over the whole real line and it's equal to 1. And because the sum of the probability of being in the green segment and the blue segment has to add up to 1, that means that the limit when we take a to minus infinity of the CDF has to be 0. Hopefully that makes sense. Okay, so on the left, it's the value is 0. On the left, I mean when we go to minus infinity. On the right, when you go to plus infinity, the value of the CDF is going to be equal to 1. So what happens in between? What is its behavior in between? Let's consider 2 points A and B where B is greater than A. And here I'm just going to paste a picture that I drew earlier. This is my picture. So now the CDF at A is the probability of being in the purple pinkish segment. The CDF at B is the probability of being in the green segment. So what we see is that we can express the interval going up to B as the union of the interval that goes up to A and the interval that is between A and B. Okay, we can do that. And now we can express the probability. Oops, I should have maybe written a little bit more here. We can express the probability of this guy as the sum of the probability of being here plus the sum of the probability being here. Let me put the picture again. So that means that the CDF at B has to be greater or equal to the CDF at A, because we can express it as this probability, which is the CDF at A as A, plus the probability in between. Okay, hopefully that makes sense. We'll get back to this point where we talk about probabilities of being in intervals. So I'm going to keep that picture in mind. Okay, so in general, this, by the way, just to make it very clear, what is this telling us? It tells us that the CDF is always non-decreasing. Okay, it cannot decrease because that would be a contradiction given this picture. Okay, the CDF at B is always greater or equal to the CDF at A when B is greater or equal to A. So CDFs in general are going to look like that. They're going to go from 0 to 1. So if you compute a CDF, either in practice for some probabilistic modeling or for a homework problem or an exam, check that it goes from -0 to 1 and that it's non-decreasing. That's an important sanity check. So now let's go to the very important question of how do we decode the probability of an interval from the CDF, because this is the whole point of the CDF. The whole point of the CDF is encoding the probability that the random variable belongs to any possible interval, because that's how we want to describe continuous random variables. Okay, so what is the probability that A is between A and B? Well, we have this picture. So we see that this probability, the probability of being here is just going to be the probability of being in the green segment, which is the CDF at B, minus the probability of being in the purple pinkish segment, which is the CDF at A. Okay, so we can, more mathematically perhaps, we're basically expressing the probability of being between -infinity and B as the union of being between -infinity and A, and then A and B. Those guys are disjoint. We can sum these probabilities. Check out the video on the mathematical definition of continuous random variables to see why this is legitimate. And we just replace those values by, what am I saying? It's not replace those values, right? So this is the CDF at B, this is the CDF at A. So now we have an expression for the probability, which is f of B minus f of A. Okay, hopefully that makes sense. And that's great, because now we see that indeed, as I promised, the CDF encodes the probability of the random variable being in any interval. We can completely describe a random variable using its CDF. And in fact, we can estimate the CDF from data if we want to model a continuous random variable using data. Just visually, if you want the probability that the random variable is here, all you need to do is take the CDF at the endpoint, the right endpoint, and subtract the CDF at the beginning. And that will give you the probability that the random variable is within that interval. An interesting case of a random variable is a random variable that has a linear CDF. Let's think a little bit about what a linear CDF means. If you want the probability that a random variable with a linear CDF, okay, so in this case, the CDF is linear between 0 and 1. Okay, between 0 and 1. It's linear in between. Let's take a look at the probability that the random variable is between A and B, where A and B are within the unit interval. This is just the CDF at B minus the CDF at A, which is just equal to B minus A. So the interesting thing here that I want you to notice is that this probability is proportional to the length of the interval. So in a way, this captures that random variables with linear CDFs. Where's the picture of the linear CDF? I lost it there. I don't know what happened. Well, this thing just jumped. Sorry about that. The CDF. So when you have a linear CDF, that means that the probability of being in any interval is proportional to the length of that interval, which essentially means that you have the continuous random variable is kind of uniformly distributed. We'll make this more precise when we explain what the probability density function of a random variable is, and we derive the corresponding probability density function. Okay, but for now, linear CDF essentially means that the probability of each interval is proportional to the length of the interval. It turns out that discrete random variables also have CDFs, because at the end of the day, the definition of CDF says nothing about the random variable being continuous, right? It's just the probability that the random variable is smaller or equal to a certain value. So what happens for a discrete random variable? Remember that the PMF, this is the PMF of the discrete random variable. It tells us the probability that the random variable is equal to each of its possible values. In this example, the probability that it's equal to -2, -1, 0, and so on. So when we consider its CDF, the CDF is the probability of being smaller or equal to any possible value. You can quickly see that the CDF is only going to change values at each of these discrete values that the discrete random variable can take. So what's the probability of being smaller or equal to -2? It's 0. What's the probability of being smaller or equal to -1? It's just the probability of -2, so 0.1. So we're going to get something constant there. What's the probability of being smaller or equal to 0? Is the probability of being equal to -2 or -1. So we get something constant there, which is 0.1 plus 0.2, and so on and so forth. So discrete random variables have this staircase-looking CDFs. But the CDF is well defined. It's just that it's not continuous because we have non-zero points of non-zero probability in between. You see a jump in the CDF, that indicates a point where you have non-zero probability, because remember that the probability of being in a certain interval is equal to the CDF on one side and the CDF on the other. So if you see a jump at a single point, that means that that point has non-zero probability. Connected to that, it turns out that a random variable is continuous if its CDF is continuous. Remember that we define continuous random variables as random variables for which the probability that the random variable is equal to each specific point is 0. So what happens if the CDF is continuous? We consider the probability that the random variable is equal to an arbitrary value a. That is basically the CDF at a minus the CDF at a minus epsilon when epsilon goes to 0. So we approach a from the left. Here, because the CDF is continuous, by definition of continuity, this is just equal to f of a when epsilon goes to 0. So this is going to be equal to 0. Okay, so an equivalent characterization of continuous random variables are those random variables whose CDF is continuous. Okay, so now let's talk about quantiles. In order to motivate the definition of quantiles, let's consider the probability that a random variable is here in this interval, where Q1 is the value such that the CDF at Q1 is equal to 0.25. By definition, the probability that the random variable is there is equal to 1/4. Now, let's consider the probability that the random variable is between Q1 and Q2, where Q2 is the value at which the CDF is equal to 0.5. Well, 0.5 minus 0.25, it's again 1/4. What about, you see probably where I'm getting at, what's the probability that the random variable is in this interval that goes from Q2 to Q3, where Q3 is the value at which the CDF is equal to 0.75. It's again 1/4. So by looking at the points where the CDF is equal to 1/4, 1/2, and 3/4, we have cut up the real line into 4, because, okay, just to be clear, there's also an interval here where the probability is also 1/4. We have cut up the real line into 4 intervals such that the probability that the random variable is in each of those intervals is 1/4. And those are the quartiles, or the 4 quantiles of a distribution. They're points that cut up the real line so that each segment has the same probability. And this is kind of useful because it allows us to quickly understand where the random variable is with what probability. In particular, the one in the middle tells us how to partition the real line so that half of the probability is to the left and half is to the right. How is that point called? You probably know already. It's the median of a distribution. So let's go to the more formal definition. The n quantiles are n minus 1 points that partition the real line into n intervals such that those intervals all have the same probability. Okay, because they have the same probability, that probability has to be equal to 1 over n. And we can define them also in terms of the CDF as in the same way that I showed you here. So the first one is going to be the value at which the CDF is equal to 1 over n, in this case 1 over 4, because we're considering the 4 quantiles, which are called quartiles. The second one is going to be 2 over n, 3 over n, and so on and so forth. Okay, this is how we can find the quantiles in terms of the CDF. This is why here we have I over n from 1 to n minus 1. As I said, the 4 quantiles, when we have 4 segments, these are called quartiles. And the one in the middle is called the median. Okay, so the median of a continuous random variable tells you the point for which to the left of that point we have the same probability as to the right of that point. Equivalently, that's the point at which the CDF is equal to 1/2. You could have situations where the CDF is flat there, and in that case we usually just take the midpoint of all the values that map to 1/2. In fact, that's the situation that we had for this CDF that I just showed you. Okay, so now we have defined the CDF and quantiles as probabilistic quantities that are well defined within a mathematical framework. But now let's switch to the statistical viewpoint where we say, okay, sure, that's great, but how do we estimate these things from data? Because I need to estimate them from data in order to do probabilistic modeling. Well, if you think about it, the CDF is a probability. It's just the probability that the random variable is smaller or equal to a certain value. So it's very natural to estimate it using an empirical probability. Okay, and that's exactly what we do. This is the empirical cumulative distribution function, which just says that the CDF at any point can be obtained as the fraction of data points that are smaller or equal to that value. Okay, so remember that we use this notation where this is an indicator function that is equal to 1 if that data point xi is more equal to a, and 0 otherwise, and we divide by the total number of data. So it's just the empirical probability of being smaller or equal to a according to the data. Notice that a doesn't have to be a data point. This is well defined for any value of a. So what happens when we do that? Actually, I'm going to draw a picture because I think it's helpful. So imagine that you have just 3 data points that are here, here, and here. How is the empirical CDF going to look like? Well, there are 0 data points to the left of this guy, so it's going to be 0. Then here, there's going to be 1 data point to the left of any of these guys, so this is going to be 1/3. Actually, I should maybe draw it as a line. Okay, so we start, I'll use blue. We start at 0. Then here we jump to 1/3, because for all of these points, there's 1 data point out of 3 to the left of them. Then here we're going to jump to 2/3. And then here we're going to jump to 1, because all of the data points are to the left. Okay, that's a staircase. I drew it a bit of a very squiggly way. I know that by now you must know that I'm a bit artistically challenged. But in general, empirical CDFs are going to look like a staircase, which is kind of interesting because that means that they're not really the CDF of a continuous random variable because of the fact that the data are discrete. Okay, there are ways of making this CDF continuous by making assumptions about the random variable, but the empirical CDF as we have defined it, if you zoom in, looks exactly like this, as a staircase where we have a jump of 1 over n at each data point. How do we estimate the quantiles? In a very intuitive way. So what is the first quantile? It's the point at which the probability that the random variable is to the left of that point is equal to 1 over n. So basically we go to the point where we have 1 over n data points to the left. So we use the empirical probability in that way. Equivalently, we look at the point where the empirical CDF is equal to 0.25. So this is easier to see with a picture. So here we see the empirical CDF. And now we want to find the first quartile. That's going to be the point at which 1/4 of the data points are here. Then the second quartile is going to be the point at which 1/4 of the data points are here. So that means that this is the median. Half of the points are to the left and half are to the right. And then for the third quartile, 3/4 of the data points are here and 1/4 are to the right. Okay, so pretty intuitive, I would say. In general, it's very useful to plot the quartiles in terms of box plots. So a box plot describes a distribution in a very concise way. It tells us where the median is, where the third quartile is, where the first quartile is, and then it gives us these lines here are usually 3.5 or it depends, right? This is a parameter, but approximately 3.5 times the interquartile range. It depends on what you decide. And if there are any other points that are beyond that, you usually show them here like outliers. Okay, so here this is the height of a population. We immediately see that half of the people are shorter than about 175 centimeters. 1/4 of them are shorter than 170. 1/4 of them are taller than 180. And then there's some very tall people that almost get to 2 meters and some very short people that are below 160 centimeters. It really quickly captures the properties of the distribution. Here we see the distribution of GDP per capita of the countries of the world, and we see that while height is kind of, I don't know how to explain this, but it's kind of regularly distributed, if that makes sense, around the median. Yeah, I think that's a good way of saying it. Regularly, I don't know if it's the best way, but I think you understand. With GDP, this doesn't happen at all. We have a massive amount of countries that are very poor. You see them here, they're all bunched up here. Half of the countries are below here. And then we can have some outlier countries, which are countries such as Luxembourg, Monaco, and so on, that are extremely rich. And then we have a long tail that you see here in terms of the values between the median and the third quartile of moderately rich countries. So very quickly, we see that the distribution of GDP in the countries of the world, I hope I said this at the beginning, that this is the GDP, the gross domestic product of countries in the world, is very, very differently behaved to the height of a population. And you can see it very quickly from the box plot. This also allows you to compare distributions. Here we use the box plots to compare the weather in Oxford in different months. So we see the median for each month. We see the interquartile range, which is the difference between the third and the first quartile for each of the months. And we very quickly see that it's warmer in the summer, it's colder in the winter, but we also see that there's more variation. You see that the box plots are a bit more spread out in the summer and the winter than in the spring and the fall. Okay, so it very quickly allows us to compare all of these distributions visually. I think it's a very useful, plot for descriptive statistics. Okay, so what have we learned? We have learned the definition of cumulative distribution function, the definition of quantiles, and how to estimate these quantities from data and then plot them. And that's all I got. Thank you very much.